In this video, we are going to talk about the electric field on the axis of a uniformly charged rod. Okay, so we have a rod, okay, a one-dimensional rod. Let's say the rod's length is capital L. Let me write it over here, capital L. And we want to find out the electric field due to this extended body, right, at this particular point P. Maybe this point P is at a distance A from this rod. Okay, I don't know, let's say A distance. Okay, so how will we find out the electric field due to the extended bodies? Till now we have seen how to find out the electric field due to point charges. When there are point charges, you can easily find out the electric field. If I have a point charge Q and at a distance R I want to find out the electric field, it is kq by r square, right? It's as easy as that. Now how will we do in such a case? See, we can think of this extended body as made up of many point charges, right? It is made up of many point charges. Now this one, this one, this one, and this one, and we can all add all these electric fields of many point charges. But now these are so many charges, right? Many charges are there uniformly distributed on the rod. So it is very difficult to take the charge one by one, right? Okay, so it will be difficult. And now the thing is, the electric field due to the charges which are closer to this point P will be higher compared to these charges. These charges will not have the same electric field at this particular point P as that of these charges. So now to do this, we have to take a small element of this charge dq. Let's call this element here as dq. This is a dq charge over here. Okay, this is a dq charge, and let's say this dq charge is at a distance x from this point P, right? This dq charge is at a distance x from point P, correct? Now this dq will have its electric field at point P, and then we will do integration. We will add all the dq charges here, the electric field due to dq charges, we will add up. So adding means summation, and summation for the continuous charge distribution will be the integration. So let's see what is the electric field due to this dq charge at this point P, right? This dq is at a distance x from point P. Okay, so that electric field will be dE, of course, because it is due to a small charge dq, right? Okay, it will be k dq by x square, right? Now one thing you should understand is that the charges are distributed uniformly, right? Let's say the total charge distributed on this rod is capital Q, right? And hence the Q by capital L is the charge per unit length, and that is constant. We'll call this as lambda, and this lambda is called as charge per unit length. Okay, charge per unit length. So charge per unit length is constant. What does it mean? It means that for a given length of this rod, there is a constant charge. Okay, suppose lambda is equal to 2. Suppose the lambda is equal to 2. In a general, in a specific scenario, the lambda is 2. This is coulomb per meter. What does it mean? In 1 meter of this rod, 2 coulomb charge is present. That's why 2 coulomb by 1 meter is 2 coulomb per meter, right? Suppose if I take a 2 meter long rod, then the charge will be 4, because 4 by 2 will be 2 coulomb per meter, right? If I take a length of rod as 2 meter, then to have lambda as 2 coulomb per meter, your charge Q should be 4 coulomb. Then and then only the ratio will be 2. So now the charge will increase in proportionate increase of the length. Okay, so per unit length the charge is constant. That's it. Okay, so this is a dq charge, and because of this dq charge, the electric field at point P, this is at a distance x, by the way, the electric field at point P will be something. So dE is k dq by x square, right? Okay, now this dq will have a small length dl. This dq will have a small length dl, of course. Now can I say lambda is also dq by dl, which is nothing but the charge per unit length. But from here dq can be written as lambda times dl. dq can be written as lambda times dl, correct? So I can write here is k lambda dl by x square. Okay, right? Let me take this length element as x, dx. Okay, because the variable is x over here, so let me take it over x. Okay, let's call this as dx, lambda times dx. Okay, now this electric field at point P, we have to do summation over, right? So k lambda is constant, so k lambda we will have 1 upon x square dx. Now let's do the integration to get the total electric field. So integration over dE will give you the total electric field E, which is nothing but integration of this k lambda by x square dx. So this is k lambda are constant, so we can take it outside, and 1 by x square dx we can integrate. Now what is the limit? The limit will be from this charge. This is the first charge that I am going to take, right? So that will be x is equal to a, right? So x equal to a, and the last charge is here, which is at a distance a plus capital L, right? So this will be a plus capital L. Okay, so if I do the integration, let me do it here. So this will be k lambda 1 upon x square dx. Integral will be, see, you know the integral, right? This is x to the power minus 2 dx. So this will be x to the power minus 2 plus 1 upon minus 1. This will be minus 1 upon x. If it is an indefinite integral, one constant will be there, right? Okay, so is it visible? Yeah, okay. So now this will be minus 1 by x plus c, but it is a definite integral, so I will not put the constant. So this will be minus 1 upon x. The upper limit is a plus L. The lower limit is, sorry, a, not L, a. So this will be k lambda minus 1 upon a plus L plus 1 upon a, because minus of minus is plus. So this will become k lambda a minus a basically plus a plus L into a plus divided by a plus L into a, right? So this will get cancelled out, right? Okay, and you will end up with k lambda L upon a plus L into a. So this is k, but lambda is what? Q by capital L, right? So Q by capital L into L upon a into a plus L. But L and L gets cancelled, you will get kq by a into a plus L. This is your electric field. This is your electric field due to the uniform charge distribution, right? Due to the uniform charge distribution on a rod. Okay, that will be kq by a into a plus L. Now, is it the correct formula? Let's see. Suppose this length L tends to 0, right? If this length L tends to 0, that means this is just a point charge, right? This is a point charge situated at A. So if L equal to 0, it is kq by a square. That is correct. If you have a point charge at a distance A from this point P, the electric field will be kq by a square. So this is the thing, right? Okay. So this was the derivation for the electric field on the axis of the uniformly charged rod. Okay, thank you.